So the goals for today, day 9, are looking at the normal distribution and the empirical rule and looking at confidence intervals specifically for population proportions. So from yesterday, I just wanted to make sure that we got the key takeaways on the central limit theorem. So we looked at that. We saw when is it appropriate. You remember there are some you have to check some things to make sure you can use it. But what's interesting is that the distribution of sample means, so we're looking at sample here, we'll talk more about that as we go along, or sample proportions, has an approximate normal distribution, no matter what the distribution of the original data looks like, as long as the sample size is large enough and all samples have the same size. I added a parenthesis here, missed that the first time. So why do we care about this? Well, we're about to talk about something called, talk about the empirical rule, and it assumes that you have a normal distribution. So if we know this, that we have this distribution of the sample means looks like it's normal, has the same shape, we can say a lot about it without having to do a lot of calculations. So you still may be saying, why do we care? Well, when we use the normal approximation, instead of a simulation based, it gives us some power. Instead of looking at the simulations, which we see change quite a bit as we move along, not that this is perfect, but it definitely gives us some other way to do it instead of having to do a simulation every time. So we're going to start, before we actually talk more about the theory here, about the 68, 95, 99.7%. It's called the empirical rule about the normal distribution. So when the distribution of a quantitative variable, we're going to start there, specifically looking at quantitative variable, appears bell-shaped and symmetric, we can say it has a normal distribution. Remember, we've talked a bit about the normal distribution before, that it has a nice bell-shaped curve and that it's very symmetric. Every normal distribution has a mean and a standard deviation. So that's SD is always standard deviation, of course. The empirical rule states, though, that 68% of the distribution, in other words, of the values, are within one standard deviation of the mean. So here we go. I'm going to note right now that within means plus or minus 1. So this is 68% of the values fall within one standard deviation. What's even more interesting is that 95%, this is the 95%, of the distribution of the values are within two standard deviations. And if you want to get almost 100%, we know that everything is within plus or minus three standard deviations. And I got this, I always remember, if you ever do post something, cite something that's not dummies, that's it's one of those yellow books. I don't know if you've seen them in the bookstore. You're like, well, how am I going to end up using this? Let's think again about sampling variability of sample proportions. So we're going to look at sample proportions specifically. When the variable is categorical, the statistic is p hat, and that's the proportion of success, however we define success in a sample. Now, p hats are going to vary from sample to sample, and we've seen this repeatedly. We can predict how p hat will vary in relation to is pi value. Let's get rid of that is. Sorry about that. We can predict how pi hat will vary in relation to the parameter value. So remember, sample proportions will have a distribution of a mean, hopefully, mean of pi, and the standard deviation is going to be pi times 1 minus pi over n. And remember, when we're defining pi, that's that parameter value, we're doing that when we're doing our hypothesis testing, right? When we first set things up. So with a shape that is approximately normal, remember, in this case, as long as there's at least 10 successes and 10 failures. This is kind of cool. We see all these little p hats in here, right? all these p hats. All of those p hats are from different, when we take different samples, okay? So we're taking, let's say, take whatever study you like that we've done so far that's proportions. And remember, we took samples again and again and again, and we generated that null distribution. Well, in the middle, we're going to say, remember we say that, of course, a mean. Let's go back up here. They have a middle, right? And then standard deviation is variability. As we go along. So from the central limit theorem, this is where that's from. Back from the previous day, this pi here, remember this is the population proportion. And this is the parameter value. Now, oops, sorry, I should have grabbed this last one here. You're going to notice all of these p hats. Remember, p hats going to vary. They're a statistic. They're going to vary from sample to sample. But what we notice is, assuming this is all based on the same study here, that this is one standard deviation away on each side, right? Now, do we notice that the vast majority, we know that 95% of the p hats are going to fall within 2 standard deviations? Would you all agree there? Just looking at it, we see that. This is really powerful. You may wonder why. Well, you know, it's very powerful as if we take any of these p hats here, is it going to be within 2 standard deviations of this pi value, at least? Yes. So we can make a good estimate of pi, that parameter value, that population proportion that we're interested in. Sometimes it's easier to see something instead of talking about theories, looking at an example. So this is we're going to take a look at a survey here. And it's about cyberbullying. In March of 2018, survey of a nationally representative sample of 43 teens between the ages of 13 to 17, Pew Research Center, once again, Pew Research Center generates very good data, found that 59% reportedly had experienced one or more types of cyberbullying online or on their cell phones. Do the data provide evidence that a majority of all such U.S. teens have experienced cyberbullying? So underline the research question. You're going to notice these first couple are done. We already did that. I already filled in some of this to save time, but remember, variable, whether or not you have experienced cyberbullying, it's categorical. You notice I didn't ask if it's binary or not, so I'm not going to worry about that. The sample is 743 teens. Hopefully, as you're going through, you can look up and see right there. The p hat was actually, we didn't have to calculate it. It was given to us, and it's described. The population, all U.S. teens. You notice this is a nationally representative sample. Hopefully we'll be able to make some generalizations, right? Once we do our look at this survey. Could we use this for teens in Sweden? No. Based on the nationally representative sample, so Pew Research Center is based here, well, at least this branch is, we're looking specifically at US teens. That's something we'll think about as we keep going. The parameter pi, proportion of all US teens who have experienced cyberbullying, or the probability the US teen has experienced cyberbullying. So you could see it either way, both are okay. Make sure that you really get these, that you understand where these are coming from, and this, because this is stuff that I'm now going to take, I'm just going to assume that you understand. So if you go back to the research question, it says, do the data provide evidence that the majority of all US teens have experienced cyberbullying? And it asks for the null hypothesis. It doesn't ask for it in words, it just says in symbols. We're talking about p hat, and already we see the parameters pi, so we know we always want to set it in terms of the population parameter. Now, the majority. The majority to mean means half. Just 1 over a half is the majority, right? So we know that we're going to be looking at 0.5. So my null hypothesis is that it's pi is equals 0.5. We want to know if the majority of teens. So are we looking at less than or greater than for the alternate hypothesis? And hopefully you automatically said greater than 0.5. So number 8 says, first use the central limit theorem to determine a standardized statistic. Then state a conclusion of all such US teens have experienced cyberbullying. Now, in general, we want to test to see if we can use the central limit theorem. Here, since it tells us just to use it, we're going to say, okay, we're just going to use it and figure this out. So we need some information first, and I know that I can pull it from above. N is 743, so that's my sample size. The null hypothesis is pi equals 0.5, and I need to calculate the standard deviation for this. And remember, that's when you take pi times 1 minus pi over n, and then you take the square root. So I'm going to plug the numbers in, and I'm going to get 0.5 times 1 minus 0.5 all over 743, and then you take the square root. And I get 0.0183 for my standard deviation. So that helps us. We know that we do this because we know that we can use a central limit theorem. We can get a nice standard deviation. And we want to find out some more. So remember, when we're looking, if we're saying we can use the central limit theorem, we know that we can draw all the p-hats are going to be in here somewhere, and it's going to center at 0.5. All right, and that's according to our null hypothesis, right? So what's a standardized statistic for this? Well, remember, it's z minus the observed value, the observed proportion, minus the null hypothesis, all over the standard deviation that we calculated. And that gives us 4.92. Whoa, that means we're almost 5 standard deviations. So that's way out here, right? Away from the center, right? So the center, of course, when we're thinking about this, this is looking in terms of p-hats and in terms of proportions. But if this is 0, this would be z equals 0, right? Because we're right at the same as the center. 5 standard deviations would be way out here. Are you way out in the tail? Yes. So what conclusion can we state? So in conclusion, you may want to pause it and write this down, but you may want me to read it first. Because the standardized statistic 4.92, which is what we calculated, is much larger than 3. Remember, we had done that z-score, looking at the z-score before. We have very strong evidence that the proportion of US teens who have experienced cyberbullying is more than 0.5. So remember, we can use that central limit theorem to get the standard deviation and to know that it is, based on the fact that we're using it, also that it has a nice bell shape. Next, because the normal approximation is valid, you can use theory-based inference applets to verify the standardized statistic and determine a normal approximation-based p-value. We want to interpret that value. So I went to the theory-based inference app, and I suggest you take a moment after you watch this and try it yourself. We know the sample size, so the scenario is a 1 proportion, so I made sure I had that selected. And the sample size is 743. The count is 438, or you could put in p-hat is 0.59. And you calculate, the sample data comes out and it shows the successes and failures. It should add to 1, right? Because we're looking at the total. The theory-based inference test. Now, when I did that, I clicked test of significance. I said my pi is 0.5. And then remember, we have to choose that, toggle that by clicking on it. We wanted to know if the majority, so greater than 0.5, and we hit calculate. So the p-hats are all within here, right? We know they're, as I point at the screen again, it calculated, and we knew it was actually, we could use the normal based approximation. Why is it valid? Remember, let's try valid again here, that we can use that normal approximation if the population is large enough, which it's obviously the number of US teens in the United States is large, but it's also valid. We need to look if we have greater than 10 successes and greater than 10 failures. And with the sample size of 743, that's pretty obvious. So that's just kind of a sidebar to remind us what we should look at. Now let's look and see what it came up with. It came up with a z-value of 4.88. That's actually really close to what we came up to. We came up with 4.92 in the previous page that we calculated by hand. So that's pretty cool. This p-value, once again, is it actually 0? No, it's just telling us it's very, very, very small. So we want to say the p-value is less than 0.001, so less than 0.1%. So the question asks us to interpret the p-value, and that's what I did here. If only half of all US teens have experienced cyberbullying, we will see 59% or more in a sample of 743 teens say they've experienced cyberbullying less than 0.1, just to make sure that's really clear, 0.1% of the time. That's pretty small. So where we want to go now? Based on the p-value, what can you say about the proportion of all US teens who have experienced cyberbullying? So here we're going to draw our conclusion. Based on the very small p-value, we have very strong evidence that a majority of US teens have experienced cyberbullying. That's sad. I have a teen. You all were, some of you are still teens. A lot of you are still teens. That's hard as a mom to see. And so please be respectful when you're online, just as a note in general. Remember though, you notice I said specifically US teens. We haven't studied teens all around the world, so we can't say anything about teens in other countries. What's the next logical question now? So we've seen more than half. My question is how much? How much of a problem is it? So what is the proportion of US teens who have experienced cyberbullying? We can use the available data to actually answer this. And what we're going to use is the empirical rule. And that's one of the cool things. Since we know the sample proportions have roughly, have a nice, beautiful, normal shape, we can go back to the beginning and remember that empirical rule that 95% of all of those observations are going to be within 2 standard deviations, gives us something. So we want to get into estimating the value of the parameter. All right. And that's where we're heading next. So you may not think that we have enough information to actually estimate that the population parameter, but we do. It takes us to the concept of estimation rather than just testing the plausibility, which is what we've been doing up to this point of particular numbers. So we tested to see if it was plausible that more than half, in this case with 59% that we were looking at for a parameter of interest. We now want to look at estimating an interval of plausible values of the parameter itself. So how are we going to go about that? So let's say what we do know so far. So let's list what we know. We do know that p-hats vary, right? So remember, under that normal distribution, every time you take a sample of the 743, you're going to get a slightly different proportion. Hopefully we all agree about that. We know that when certain validity conditions are met, the distribution of p-hats is normal with a mean of pi and a standard deviation of the square root of pi times 1 minus pi over n. Remember, that's from that central limit theorem. So now, we know these things, and hopefully we all agree on these first two. Assuming the normal approximation is valid for the distribution of p-hats, for true or false, for 95% of random samples, the p-hat will fall within 2 standard deviations of pi. True or false? Hopefully you said true. All right. I just paused and went back up to scan back up really quick to our page 53 of the notes already. Remember, we had that normal distribution. We have it drawn here, and we started talking about it. We said this p-hat is going to be within 2 standard deviations. Is that true? Yeah. So any of these p-hats will be within 2 standard deviations. 95% of them, right, of p-hats will be within 2 standard deviations? Yes. Does that 95% feel like a pretty good number? It does to me. That seems like most of them. I mean, it only leaves 5%, some oddballs that are out here in the tails. Going back to where we were. So yes, based on that empirical rule that we have been given, we know that if we're looking at this, and I have the normal distribution, okay, it could be prettier, I know, that I've got pi that here, if I say this is pi plus 2 standard deviations, and this is pi minus 2 standard deviations, 95% of the p-hats, so those samples, are going to fall within there. All right. So we can say a very reasonable location for our sampled p-hat is within 2 standard deviations of the mean of the distribution. In other words, pi, right? Because the mean of this distribution, so we're still talking about proportions, but remember, this has a center, right? So this curve has a center being a mean, center being average, and that is the value pi. So let's think about this. By that same logic, a very reasonable location for the true value of pi is within 2 standard deviations of our sampled p-hat. And that's what I've been working at, right? As I've been talking about this, trying to convince you. So what if we did this? We have p-hat plus or minus 2 standard deviations, and we say pi here, but wait, we don't know pi, right? In theory, we've been using our hypothesis, the null value, what it equals. We don't know pi then. So we can use p-hat in its place. All right, because we want to get to where exactly, we've been using that to when we come up with standard deviation, when we come up with standard deviation, we've been using pi. But we know that there's going to be that our pi will be, remember we talked about being within 2 standard deviations. At this point, we don't have this value, right, in theory, because we don't know exactly, and up to this point, we've just been plugging in whatever the pi is. But we can use p-hat in place of pi. So the general form for 95% confidence interval for pi is Here we go. The center, this would be hopefully what our value are, we're going to use for our value of pi, plus or minus 2. Ooh, this gives us a really good interval that is going to most likely include the true value, or the true proportion, true being in this case being the value of the parameter. So the true value of the parameter, true being the real what it actually is, which we can never know, right? Because we're always taking samples trying to make guesses. So a confidence interval is a confidence interval is an interval of reasonable, based on our observed data, values for the parameter of interest. We calculate a confidence interval from available sample data. So how do we compute confidence intervals in general for populations? So we're looking specifically at proportions right now. We can compute the Z confidence interval right here. We want to be 90, 95%, or 99. You're like, why don't we just do one standard deviation? Well, being 68% confident isn't really that good. I mean, let's be honest here. 90% is, if we do that Z, is 1.645. 95% is, we're going to use this Z star. This is not the same thing as the Z. I know there's lots of Z's and P's right now. This is not Z, that standardized statistic. This is Z star, which are right here. So we're going to multiply that by that standard deviation we come up with. 95%, instead of 2, we actually can do better. We can do 1.96. It's more, it's closer. And 99%, if we want to be super confident, the Z value is going to be 2.576. Now the margin of error is this right here. This is the margin of error. So the margin of error is how researchers report how much variability they anticipate in the estimated numeric value of the parameter based on the sample size and how confident they want to be in their sample. Now, if you want to be really confident, you want to make sure you get something. So just thinking about this, and you have it, and let's say the center's here. I'm not even going to label it, just say it. If you want to make sure you get more, you're going to, let's say you want that 99, you want to be really, really certain. You want to be 99% certain. That's pretty broad confidence interval, isn't it? What if you were only worried about being 90%? Well, that would be in here. Which confidence interval is wider? The 99, because you want to be really certain that you get that parameter value in there. All right, so when estimating, going back to the notes here, a population proportion, the margin of error is Z star times that standard deviation we calculated using specifically the sample proportion. So going on, let's continue on with this example. So let's look back at the cyberbullying example. First of all, we're going to verify that the normal approximation is valid. Remember, for proportions, what we want to do is take the number of successes, which is going to be 0.59 or 59% times, this is n, the sample, and that gives us 438. That's a lot bigger than 10. We also have to look, remember though, at the number of failures. We could have, I mean, it's pretty obvious here, you can see it, but it's good to show it. So I did 1 minus 0.59, in other words, because your number of successes plus your failures has to total 1 when you're looking at percentages, or 100%. So I had 0.41 times 743, which gives me approximately 305, which is definitely greater than 10. And we know that we have a large population. That's easily 10, 20 times as big as 743, because there are a lot of teens in the US. Now we want to estimate the 95% confidence interval for the proportion of all such teens in 2018 who've experienced cyberbullying. So we want to actually calculate that. This is where you need to be a little bit careful because remember, it's a slightly different formula. We're going to, if we're coming with a confidence interval, what is the center of the interval, by the way? Where would it be? It's always going to be right at the p hat. All right, so if you were given an interval and asked to find the center on the homework or whatever, you could take each of the ends, add them together, and divide by 2. Get you right back at the center. So I know that p hat equals 0.59, and it asked me to find a 95% confidence interval. So I'm going to do the 0.59 plus or minus. Now, go back up here. Oh, let's see, 95%. I'm going to use the 1.96. Square root, and then literally, I don't want to say plug and chug, but fill it in. And you're going to get 0.59 plus or minus 0.035. Are we done? We don't have a confidence interval, but we do know our margin of error, right? We calculated it right there. There's our margin of error. And actually, I think, what's the margin of error? Oh, we saw it right there. So now I'm going to add, I'm going to subtract the 0.035, and I come up with 0.555. Then I'm going to add it, and I get 0.625. You're going to notice I wrote it right here, but I just wanted to make sure you could see the calculation. So we are 95, interpret the interval. I had this typed in because I really wanted you to think about it. We're 95% confident the proportion of all U.S. teens in 2018 who have experienced cyberbullying is between the true value, the true value of the parameter, what the parameter actually is between 0.555 and 0.625. That's a little disturbing because 0.625, that's over 60%, so that's a lot. And of course, we found that margin of error. So if you're struggling with this, take a read through it again. We're going to do more with this in the next video.